Welcome back, everyone. So I guess there's two quick announcements, right? Hopefully everyone saw that the TA will have a problem session this Friday. Everyone got an email about it. So if you're struggling a little bit with the implementation of Newton's method, you should stop by. His plan is to do an example, maybe two examples, to give you a little bit of help on the homework if you need it. The other announcement is that homework 2 is graded and is now available, so you can check your score on eLearning. Again, if you have any questions about the homework or the homework grading, please contact the TA. I'm still working on the midterm, so apologies there. It's taking me a little bit longer. I've just had too many other things come up this week, but I'll really try to get them done as soon as I can. Today we're going to continue on with our discussion of the singular value decomposition and its applications. So where we stopped last time was basically the definition of the Morse-Penrose pseudo-inverse. So essentially what we had seen in an earlier lecture was that the solution to a linear system was essentially given by well, the least square solution to a linear system, right? So assuming that there was an x such that ax equals b, the x of smallest norm, at least 2 norm, was given by a somewhat complicated looking formula. So this little formula here in the bottom left, where this D plus matrix was a diagonal matrix whose elements are the inverse of the non-zero elements of the diagonal matrix D. So this little plot came up when we were trying to solve, when we basically wrote down the equations to solve the linear system, assuming that a solution existed using this eigenvalue eigenvector factorization that we got for symmetric matrices of the form AA transpose. What we saw last time is that using the singular value decomposition, we can simplify this formula and end up with something a little bit more aesthetically pleasing. So namely, if A has a singular value decomposition U sigma V transpose, then we could define the matrix A plus, which we call the pseudo-inverse of the matrix A, to be V sigma plus U transpose, where again, sigma plus is the diagonal matrix whose non-zero elements correspond to the inverse of the non-zero elements of the diagonal of the matrix sigma. We saw last time that this lines up with the correct intuition if the matrix A happens to be invertible. If it's not invertible, it's sort of the closest thing to defining the inverse, basically over the range of the matrix A. So those vectors that span the non-zero eigenvectors, that span the eigenvectors that have non-zero eigenvalues of the matrix A. Good. Were there any questions about the SVD or the pseudo-inverse from last time? So I think I can't remember who it was, but someone had asked to see some examples, so that's what we're going to do today. The question is, there's a question in the chat. If we prove that A is invertible, then the pseudo-inverse and the inverse, I assume yes, the inverse, yes, are synonymous. Yes, you can interchange them however you want if the matrix A is invertible. If it's not invertible, though, this A plus thing will give you a solution, the solution to the linear system Ax equals b of smallest norm, if such a thing exists. We'll prove something slightly stronger today, namely that the pseudo-inverse actually always does something nice, even if the linear system doesn't have a solution. So we'll see that today as one example of applications of the pseudo-inverse and the SVD to the kinds of optimization problems that we've been looking at in this course. Other questions about the pseudo-inverse, its definition, or the SVD or anything that we saw last time? Okay, well then let's do some examples. Like I said, so today I prepared just a couple different example applications of the pseudo inverse and sort of related ideas to do like the theory of optimization that we've been looking at in the course. So it's this discussion today is a little bit more complicated in the sense that a lot of the examples we've seen, using the theory of Lagrange multipliers, the dual was sort of somewhat straightforward to work out. We basically just took some derivatives and everything worked out nicely. What we'll see today as examples of some of the tougher cases of when we end up with more complicated dual solutions or dual constraints that we have to massage a little bit to put them sort of in the right form. So I'll explain as we go along. Let's take a look at the first example. So this is just an unconstrained optimization problem. Let's suppose that, I should say Q is an arbitrary positive semi-definite matrix. So let's suppose that someone gives us a quadratic minimization problem where Q here is an n by n positive semi-definite matrix, and S is just an arbitrary vector. So this is a convex optimization problem, right? So we know that this is sort of in the nice family of optimization problems, right? In particular, it's unconstrained, so we could try to minimize this just using gradient descent, right? So when we compute the gradient of this function, right, we get gradient of respect to x is just equal to qx minus s, right? So we could easily do gradient descent here, right? It's the update's pretty straightforward. We just plug in, we do some matrix vector multiplication, subtract s from it, and then perform the standard gradient descent update. In particular, right, we know that function's differentiable, that if there's a place where the derivative is equal to 0, so the gradient is equal to 0, it must be the case that this is the global optimal. So the question in the chat, how do we know that this is a convex quadratic minimization problem, just given the problem? Well, we don't. The reason I know that it's convex is because the matrix Q is positive semi-definite. And remember that for twice continuously differentiable functions, they're convex if and only if they're Hessian matrix. So the matrix of second partial derivatives is positive semi-definite. And in this case, the Hessian matrix is the matrix Q. So that's how I know that this is a convex optimization. So it would be non-convex if you were just allowed to plug in an arbitrary symmetric matrix. We'll talk about that case too in a little bit. But let's start off with the convex case because it's a little easier. So there's two possibilities for this convex optimization problem. So either there is a place where Q times X is equal to S, right? So that means that there's a place where the gradient is equal to 0, or this optimization problem is unbounded, so that the infimum over all possible X is actually equal to negative infinity. So to give you a little bit of intuition about how the second case could occur, it helps to just, if you have a sheet of paper in front of you, just roll it into a U shape. So that function is essentially convex no matter how you tilt the paper in space. So you imagine, right, it has an infinite set of, if you hold it sort of so that the top of the U is flat, that function has an infinite number of solutions. But if you tilt it slightly, right, it has no place where the gradient is equal to 0. Right? It just runs off to either positive infinity or negative infinity along that line. So the same thing is true here, right? So either there's a solution with q times x equals s, or we can make the objective function as small as we want without bound. So the way that we sort of prove this, algebraically, right? It somehow makes sense. Well, the first part I hope makes sense, right? That if there is a the derivative is equal to 0, right? Because it's convex, we know that's the global optimum, right? The question is that if there's not such a place, right? How do we know, right? For quadratic functions, at least, right? That the function must run off to negative infinity. So let's suppose that there is no solution to qx equals s. So what does that mean algebraically? So again, Q is a symmetric matrix, right? So that means it has some decomposition of the form, right? Q is equal to, I shouldn't have used Q here, I guess. Let's just say U d U transpose, where D is a diagonal matrix and U is the orthogonal matrix whose columns are the eigenvectors of Q. So what does it mean that there's no solution to this the system Qx equals S? Well, the only way that can happen is if X has some component along an eigenvector, one of the eigenvectors of Q, it has a 0 eigenvalue. Why is that the case? Well, if you're, let's just take the simplest example, right? If X itself, if S itself was an eigenvector of Q, right? And let's suppose that S is an eigenvector of Q with eigenvalue 0, right? Well, there's nothing that Q multiplies. There's no vector that Q can multiply that gives back S, right? Because anytime you pick any, anything that has any component along S, right, it gets mapped to 0 under Q, and all the other eigenvectors are orthogonal to Q. So the only way that this linear system has a solution, so Q times X has a solution, Q times X equals S has a solution if and only if there exists, well, I should say that for all, so I'm going to use this little upside down A as my is the standard mathematical abbreviation for all. For all I such that dii is equal to 0, it must be the case that S transpose xi is not equal to 0, or is equal to 0. To be equal to 0. What that says is that there's no eigenvector with 0 eigenvalue, such that when S is projected along that eigenvector, it's equal to 0. It has to be equal to 0. It can't have any non-zero component along that direction. To see sort of really formally algebraically why that's the case, right? Again, let's take the simplest case and suppose, without loss of generality, it doesn't actually really matter here. Let's suppose that that S transpose xi is not equal to 0, and dii is equal to 0, right? So the complement of the statement I've got down here, right? So let's take a look at the value of the objective function, right? When I plug in xi, right, as a possible x. So 1/2 x transpose q, 1/2 xi transpose q times xi. That's just equal to 0, right? Because xi is an eigenvector of q with eigenvalue 0. And the rest of the objective function then is just minus S transpose xi, which we know is not equal to 0, right? Which we just assumed there is not equal to 0. Well, because it's not equal to 0, it's just a linear function, right? Linear functions are unbounded, right? So I can take xi and I can multiply it by some constant c. So replace xi with c times xi. This first term, 1/2 c times xi transpose q times c times xi is still equal to 0, Now I can make minus C times S transpose I as large or as small as I want, depending on the sign of S transpose Xi. So if there is such an eigenvector, with zero eigenvalue and S is not orthogonal to it, basically the quadratic term disappears. I can make it so that the quadratic term disappears, and that in the linear term, right, I can make it as large or as small as I want, right, because it's just a linear function. Okay. So then there are only two possibilities, right? Either this linear system has a solution, so that S has no component along an eigenvector that has a zero eigenvalue, or the solution to this optimization problem is negative infinity, because I can just make the objective function as small as I want. Okay. Everyone happy with this argument? It's kind of important because it's going to be the sort of the linchpin for. I'm going to sort of slowly build up to more complicated arguments, but this is sort of one of the basic facts that we're going to need when we get to some of the more complicated cases. This is a really useful argument too, as well, useful and important property too. What we'll see in a minute. For example, if we end up with a Lagrangian that's quadratic, right, we'll be interested in taking infimums, right, unconstrained infimums. So we'll see this observation arise again. And again, like I said, in pictures, right, you should think of the solution here. I mean, I can try drawing it, but when there is no place where the derivative is equal to 0, you kind of get a function that looks like this. Sort of my best artistic representation of what such a function would look like, right? So we're talking about here really is this line at the top of this function. And the slope of this line will dictate whether or not this convex quadratic function has a solution or not. Right? So that's what the picture looks like in this particular case. Right? If there's no x such that qx equals s, this little like U shape is just tilted in space, and it's possible to make the function run off to plus or minus infinity. So this is what the picture would look like in 3 dimensions. Of course, it's very hard to visualize in 4 dimensions because there's multiple different ways that the function can run off to infinity, negative infinity. Oh, I drew the picture backwards, actually. Apologies. Convex function would look like this. I drew the concave version. So the convex version would look like this. Sorry. It'd be upside down, right side up U shape, not the upside down one. Okay. Questions about this argument? Everyone happy with it? Okay. So if you're happy with this argument, there's sort of one nice simple consequence of this that applies to the pseudo inverse. Let's take a look at that. So here's a quadratic minimization problem. Minimize over all n-dimensional vectors of a x minus b. So here we're saying, say A is an n by m matrix. So when you multiply A, or let's say n by n, just to make my life simple for a minute. It doesn't matter if it's square or not. To make my notation line up, either I want it to be x and a to have the same number of rows, or no, I guess not. It could be it needs to have the same number of columns. So let's say a is m by n. That would be the general case, I guess. So someone gives us this matrix A and some vector B. Again, so B here has to be m-dimensional if A has m rows, right? Because then A times x will be an m-dimensional vector. So someone gives us these two things, right? The matrix and the vector. Right? And the aim here was to find the solution to the system AX equals B. But if one doesn't exist, this optimization problem, of course, still has a solution. it's convex, and it's bounded from below, right? Because the norm is always greater than or equal to 0, right? Because it's the square root of the sum of the square entries of this vector. It's always non-negative. So we know, for example, right, that we can't be in case 2, right? So if this was case 1, this is case 2. We can't be in case 2, right? Because in case 2 here, the solution would be negative infinity, but that's not possible, right? Because this thing is bounded from below. So let's expand that. Let's expand the definition to see what the quadratic form actually looks like. So when we do that, we write the 2 norms squared as ax minus b transpose times ax minus b, yes, because the norm of a vector x squared is just x transpose x. And then multiplying that out, we get x transpose a times x minus 2b transpose a times x plus b transpose b. And as I just said, either a transpose ax is equal to a transpose b has a solution, or the norm here has to be equal to negative infinity. But like I said, we can rule out the second case because we know that the optimization problem is bounded from below. So how is it possible that we always know that this thing has a solution? Well, the reason is that let's assume A was symmetric for a second, right? The argument would say something like, when we multiply both sides of this equation by A transpose, it effectively zeroes out any components of B that are along bad directions, right? So if for example, if B has a component along an eigenvector of A transpose A that's equal to 0, the A transpose thing will effectively kill off that the component along that direction. So that's sort of the difference between solving the system AX equals B and solving the system A transpose AX is equal to A transpose B. This system always has a solution, whereas AX equals B does not necessarily, right? Depending on whether or not B exists in the right space. Good. So let's see what the solution is then. Right. So we, under the assumption that this linear system has a solution, we know how to define that solution, right? We just construct the pseudo inverse of A transpose A, right? That will give us a solution of minimum norm. So let's assume that A has a singular value decomposition of U sigma V transpose. Then A transpose A, right, is equal to V sigma U transpose times U sigma V transpose. And so the U transpose U is the identity matrix, and we're just left with V sigma squared V transpose. The pseudo inverse of this thing, that's a transpose, not a squared. The pseudo inverse of this thing is just we take the matrix sigma squared and invert all of its non-zero diagonal entries. But that's the same thing as just taking the non-zero diagonal entries of sigma and inverting them. So the pseudo inverse of this thing is just equal to V times sigma plus squared times V transpose, where again sigma plus is the pseudo inverse of the diagonal matrix. Then A transpose is just equal to V sigma U transpose. So all I did was use the singular value decomposition and the definition of the pseudo inverse here to construct the second line. Now again we've got V transpose V, so that's the identity matrix. So those cancel out. I'm left with V times sigma plus squared times sigma times U transpose. But sigma plus inverts the non-zero entries of sigma. So when I take sigma plus and multiply it by sigma, I get a diagonal matrix of all ones and zeros. The ones are in the locations where sigma has a non-zero entry. So then sigma plus squared times sigma is just sigma plus. Yeah, there's a question. How did we get sigma plus? So how did I construct the pseudo inverse of this matrix? Yeah, so it's the pseudo inverse of V sigma squared V transpose. Right, so the pseudo inverse of this thing is V sigma plus squared V transpose. That's just the definition of the pseudo inverse. This is a symmetric matrix. Right? Is that what you're asking? I make sure I answer this question. Yes. I'm sorry. Right. I multiplied. I use the fact that the solution to this linear system is given by the pseudo inverse of A transpose A times A transpose times B. Yes. Sorry. Right. Remember that it's not. I didn't go from like this equation to the first one here by multiplying both sides by A transpose A pseudo inverse. Right. That because although that's kind of technically what I did, right? I'm using the observation here that I know that this is a solution to that linear system, right? It's the one of minimum norm. Continuing with the algebra, right? I end up with just simplifying this expression. I end up with V times sigma plus times U transpose times B, but that's nothing more than the pseudo inverse of A by definition times B. So what we actually just showed here was that the solution to the optimization problem, so if I scroll back some slides here, find the value of x that minimizes ax minus b, norm squared. That's also given by taking the pseudo inverse of A times B, right? So now we have two characterizations of the pseudo inverse. If there exists an x such that ax equals b, right? The pseudo inverse was the solution of minimum norm, right? So that was our first characterization. Now we have a second characterization. Regardless of whether or not the linear system has a solution, right? The minimum of this expression with respect to x is given by x is equal to a pseudo inverse b. It's the same thing over here. The solution was given by x is equal to a pseudo inverse b. So in fact, the pseudo inverse always makes sense. It always gives us back a minimum norm solution to ax equals b if it exists. And if it doesn't exist, right, it gives us the back in x. It gets us as close as possible to b when multiplied by a. So that's just a nice example. So this is sort of a first nice example of applying the pseudo inverse, right, to approximately solve a linear system. So the pseudo inverse is super useful in the kinds of problems that we're solving and just sort of optimization in general when we're dealing with quadratic forms, because we'll often end up with equations, right? Linear systems when we take derivatives, and we'll often need to solve them. So that's basically why it was invented, among other sort of useful properties it has is basically its utility for being a good surrogate for the inverse in these kinds of quadratic problems. Other questions about this argument? Okay. If there's no other questions, I want to do a more complicated example, and then I'm going to do an even more complicated example after this. So we're going to sort of layer on the complexity as we go along here. So the next example I want to take a look at is the first example we saw of a again, that should be a Q of a convex quadratic minimization problem, right, was unconstrained. Now I want to slightly modify the problem, right, and add a constraint. So here I'm just adding a simple lower bound constraint that we'd like to minimize this quadratic function subject to the constraint that x is greater than or equal to 0. So to do this, I can apply the method of the multipliers. Right? So I have a collection of inequality constraints, one for each dimension of x. That means I have x is n-dimensional, so it means I have n Lagrange multipliers. So the Lagrangian for this problem takes the objective function, 1/2 x transpose qx minus s transpose x, and subtracts from it a minus lambda transpose x, where lambda is a vector of Lagrange multipliers corresponding to the inequality constraint x is greater than or equal to 0. So remember, right, if I want to construct the dual function here, the next step would be to compute the infimum, so g of lambda here is equal to the infimum over x of L of x and lambda. We basically just saw how we solved this optimization problem, right? Because this is an unconstrained quadratic minimization problem. So we know what the solution is. So there's two possibilities, right? It's equal to, well, if there's a solution such, if there is an x such that q times x is equal to s plus lambda, then I get the solution just by plugging in the pseudo inverse, right? If there is no such x, then the solution is negative infinity. So it's negative infinity if no x such that q times x is equal to s plus lambda, right? And otherwise, it's equal to just 1/2. I substitute in x is equal to the derivative of this thing is q times x minus s minus lambda equals 0. Right, so solving for x, right, under the assumption that there is a solution here, right, the solution is given by the pseudo inverse, right, so I just plug in x is equal to the pseudo inverse of q times s plus lambda. So I get q plus times q plus transpose, but the q is symmetric, so the pseudo inverse is symmetric. So q plus times s plus lambda oops, get it backwards. S plus lambda transpose times q plus the t, the plus times q times q plus times s plus lambda. That's the first term. After I plug into the Lagrangian, and the second term looks like minus s plus lambda transpose times q plus times s plus lambda. Right, and again, I get that just by using the analysis that we just had. Right, this is the infimum of an unconstrained quadratic. It's either equal to negative infinity if there's a place where the derivative, unless it's equal to negative infinity if there's no place where derivative is equal to 0, right? Which corresponds exactly to the situation where there is no solution to the system. Q times s is equal to s plus lambda, and otherwise the solution is given by x is equal to the pseudo inverse of q times s plus lambda, and I just plug that in and simplify. Get g. So another way to write this is that the dual problem is equal to the maximum over all lambda of the expression I get when plugging in the x is equal to q, the pseudo inverse of q times s plus lambda, subject to the constraint that lambda is greater than or equal to 0, and that there exists an x that solves the linear system q times x equals s plus lambda, right? Because if there's no, in the dual problem, we're always maximizing, right? So if there's no solution to the that linear system, then we get the dual problem takes the value negative infinity. We can treat that as a constraint, right? Because the maximum can never be attained at negative infinity unless the problem is that the actual solution is equal to negative infinity. Because if there's any value, anything that satisfies these constraints, then we would be done automatically. Simplifying the objective function a little bit. So last time we saw, for example, that q plus times q plus is just equal to q plus. So simplifying the objective function of the dual, I get that the dual optimization problem is maximized over lambda greater than or equal to 0 minus 1/2 s plus lambda transpose q plus times s plus lambda. Again, subject to the constraint that there exists an x such that q times x is equal to s plus lambda. I'm going to pause here for a second and make sure that we all agree, right? What's weird about this is that I have this kind of dumb constraint in the dual optimization problem. I say it's dumb because when you look at that, it's not immediately obvious that that is actually a convex constraint, right? It's not obvious at all, right? I mean, we have to do a little bit of extra work to turn it into a convex constraint, which we'll do in a second. But I want to make sure that we're all happy with this first, right? So either this thing is equal to negative infinity if there's no x that satisfies q times x is equal to s plus lambda, or we solve this quadratic minimization problem over the lambda is greater than or equal to 0. A bit of notation. Which first term? The question, how do we get rid of the first term? In this expression? Here. So I'm using the fact that q plus times q plus is just equal to q plus. You can verify that just by plugging in the definitions. And then the first term is then equal to the second term. It's 1/2 of the second term. The second term is negative and the first one is positive, so I get 1/2 minus 1 times the same thing. So I just get minus 1/2. This basically always happens when you have these quadratic functions in your primal problem, or if the primal problem is just a quadratic, that you always end up with something that looks like this. So the question is then, how do we deal with this constraint, right? Because the lambda greater than or equal to 0 constraint is easy to handle, right? In some sense, right? We can do projected gradient, for example, if we wanted to solve this optimization problem. But this first constraint, there exists an x such that qx equals s plus lambda, but we don't know how to handle that constraint. At least, like I said, without converting it into something else first, because it doesn't look like it's convex. So let's see how we handle that. So again, the observation is similar to what we used in the previous example. So remember there, right? I used the fact that this linear system has a solution, right? Q times x. There's a solution to qx equals s plus lambda, as long as there's no basically component of s plus lambda along an eigenvector of q that has a non-zero eigenvalue. So I'm going to use the same observation here to rewrite this constraint. Maybe if my PowerPoint slides start responding again. There we go. Okay. Sorry for it's frozen for a second. So hold on. Okay, come on. Okay. So one way to rewrite that constraint is, like I just said, so q times x equals s plus lambda has a solution as long as
S plus lambda is in the span of the eigenvectors with non-zero eigenvalues, right? That means it can be written as a linear combination of things that span the range of Q, right? Again, the bad situation here is when I project S plus lambda onto an eigenvector that has a zero eigenvalue, then there won't necessarily be a solution to the, in fact, there won't be a solution to the linear system, right? So I restrict myself to S plus lambda being in the span of the eigenvectors with non-zero eigenvalue. So I can write that in sort of a more aesthetically pleasing kind of way. Let's suppose that Q has an eigenvalue decomposition of the form Q is equal to the sum over all I of mu I times xi transpose. So here xi is the ith eigenvector, mu I is the corresponding eigenvalue. So our standard eigenvector eigenvalue decomposition. So again, what I mean by it doesn't have any component along an eigenvector with eigenvalue 0 is the following. For any eigenvalue mu, if mu I is equal to 0, right? So if the ith eigenvalue is equal to 0, it must be that S plus lambda transpose xi is equal to 0, right? So that S plus lambda, right, is orthogonal to that eigenvector. So now what I've done is I've taken this constraint, right? It's sort of a weird constraint because I add constraints. How many constraints I add depends on the matrix Q, right? And how many zero eigenvalues it has. So for example, if Q is invertible, I won't add any constraints, right? There'll always be a solution to that linear system, right? But if Q has some zero eigenvalues, I add, let's say it has two eigenvectors that have a zero eigenvalue. Now add two constraints, right? That S plus lambda has to be orthogonal to basically the span of those eigenvectors. These are linear constraints, though, right? Xi is technically just a constant here, right? I mean, it's an eigenvector of Q, but I would construct it, right? I would compute the factors A Q in terms of its eigenvectors and eigenvalues, and then add the appropriate constraints to this problem. These are just affine constraints on lambda, right? Another way to write this is that lambda transpose xi has to be equal to negative S transpose xi. Right, so S here is a constant, xi is a constant. So this is just a standard, linear equality or affine equality constraint on the vector lambda, which of course is convex. It's a convex function. So we can put this problem in our standard form then. Questions about this? So the nice thing that we get here again is that we're using sort of the fact that when linear systems have solutions, it's given that there's always one given by the pseudo inverse. So that's how we get the dual function basically as a function of the pseudo inverse Q, right? And we're using this additional observation that when we end up with a constraint that says something like some linear system has to have a solution, we can replace that with a collection of convex constraints that just correspond to saying that some vector has to be orthogonal to all of the eigenvectors with a zero eigenvalue. This was a little bit of a weird transformation, but I want to pause here and make sure that everybody understands why this is the correct. There might be other ways to transform it. This is one way to transform the problem. Questions? Okay, well, if one comes to mind, please do ask. So the next example I'm going to do is even more complicated than this, involves even more complicated sets of constraints, and a more complicated dual formulation that will require us to think a little bit harder than this problem. That's why I want to make sure. That's why we've kind of been doing it in steps. Right? We saw the first example where we saw how to handle the minimization of an unconstrained convex quadratic function. In this example, we saw how to handle the situation, right, where we end up with a constraint in the problem, but some linear system has to have a solution. What we're going to take a look at in the next example is what happens when we look at quadratic minimization problems where the matrix Q is not required to be positive semi-definite, so that we don't have a convex function. Right? We cheated a little bit, right, when we were minimizing the Lagrangian, right, because when we know it's convex, there's sort of nothing else to deal with, because when we took the derivatives, we can just take the derivatives and set it equal to 0 and solve, right? So either there is a solution, or the solution was equal to negative infinity. All right, so last chance. Questions about anything that we've seen so far before we move on to the final, more complicated example? Sure, go ahead. The one on this slide? Well, no, these are convex. That's a convex formulation of the problem, right? Right. It helps in that sense, right? So once we've formulated into a standard form, right? It's now we're just talking about minimizing a quadratic function subject to a set of linear inequality and equality constraints. So now we're talking about a standard quadratic programming problem, right? So either we apply one of our constrained convex optimization problems, right? So like projected gradient or something, right? Or Frank-Wolf to solve this problem, right? You can also, like you're doing on the homework, right? You could solve this problem with an interior point method, or anything else. Basically anything that can solve these kinds of minimization problems, sort of to constraint. So that's what we would do next. Right? We'd solve this problem using using one of our existing, one of the existing tools from our toolkit. Now, granted, in this particular case, right, the dual problem is just as complicated, probably even more complicated than the primal problem. This example was just to illustrate, right, how we construct the dual in this situation. Not necessarily suggesting that that's how you would solve this, that you would solve this optimization problem that way. Okay. Other questions? So in the next example, we'll see that actually the dual problem is easier to solve than the primal problem, in some sense, but not in this case, necessarily in this case. It really depends what the constraints look like, actually. Okay. So as the sort of final example of applications of like the pseudo inverse to these optimization problems, let's consider a non-convex quadratic minimization problem. So here I want to minimize x transpose ax plus 2b transpose x, where A is just some arbitrary symmetric matrix now, So it doesn't have to be positive semi-definite, so that this is not necessarily a convex optimization problem. And I want to minimize it subject to the constraint that x transpose x is less than or equal to 1. So this optimization problem is sort of well defined. It has a solution, right? Because x transpose x less than or equal to 1 means that I'm optimizing over vectors x with with length 1, with length at most 1. So this is sort of a closed convex set. Right? It's the unit sphere essentially in n-dimensional space. So there is a solution to this optimization problem, but it's non-convex. So it's bounded but complicated. What I'd like to show here is that the dual problem is somewhat easier to solve, and in fact, in this particular case, well, I don't know if we'll prove it, but in this particular case, actually, strong duality holds, even though the primal problem is non-convex. So this is similar to an optimization problem that you have on the homework, with a few additional complicating details that you don't have to deal with on the homework. But I thought I would do this example because it drives home one additional something interesting happens here that doesn't happen in the other two cases. So we'll address that here. So the real difference in the optimization problems we were looking at before is in this particular case we have both a quadratic objective and quadratic constraints, and that was not the case in the previous example. Okay, so let's do the same thing. Let's construct the dual of this optimization problem. Again, we'll use the method of Lagrange multipliers. So here it is. I take the objective function and I add to it Lagrange multiplier lambda. Oops, a y there. That should be a lambda. Lagrange multiplier lambda multiplies the constraint x transpose x minus 1 less than or equal to 0. Rearranging the terms, I have an x transpose x. That's the same thing as like x transpose times the identity matrix times x. So I'll use I here for the identity matrix. So I can put the x transpose ax term together with the x transpose x term to yield x transpose a plus lambda I times x plus 2b transpose x minus lambda. Okay. Again, right, to construct the dual problem, I want to minimize the Lagrangian, right, over all possible vectors x. So again, the Lagrangian is an unconstrained minimization problem, right? When I take the derivative, I get that I have to have what? 2. I don't know why my screen is freezing today. 2a 2 times a plus lambda I times x plus 2b has to be equal to 0. In other words, I have to have that a plus lambda I times x has to be equal to minus b. So either there is a vector x such that a plus lambda I times x is equal to minus b, right? So that there's a solution to this linear system, right, where the gradient, so this is basically the gradient of the Lagrangian. So either there's a place where the gradient is equal to 0, or, right, from our previous argument, the thing is unbounded from below. So if there is a solution, right, I know I can find that solution by taking the pseudo-inverse of a plus lambda times I. And multiplying it by minus b. So, so I'll do the same thing, right? I'll substitute in just like I would have done before. I can cheat a little bit here in that, oops. I just said that. I can cheat a little bit here if, in this particular case, I'm going to simplify the objective function, and basically by plugging in, right, x is equal to the minus a plus lambda I, the pseudo inverse of that thing. So let me do that. I'll plug it in and simplify to construct the dual problem. Okay. I'm a little annoyed with my tablet that it keeps like switching to some. I don't know if it's just stuck in some weird mode. Okay, hopefully that fixed it. Okay. So when I do that, just like for the previous example, right? I substitute in x is equal to a plus lambda, pseudo inverse of a plus lambda I times a minus b. I substitute that into the Lagrangian for x, and I get that the dual function is maximized subject to lambda greater than or equal to 0. Right? It has to be greater than or equal to 0 because it corresponds to an inequality constraint of this big mess, subject to the constraint that, well, there's one additional constraint that I skipped ahead with. What we just showed was that the result that we had from before was if a plus lambda I is positive semi-definite, there is a solution, right? Either if a plus lambda I is positive semi-definite, then either a plus lambda I times x equals minus b has a solution, or the problem is unbounded from below. So if a plus lambda I is not positive semi-definite, there is never a solution to the minimization problem, right? Because let's just take the simplest example, right? In one dimensions, let's suppose x was just one dimensional for a second, right? If I asked you to minimize minus x squared, this is an unbounded problem. It's not a convex function, and any non-convex quadratic is always unbounded from below. So the dual problem has the constraint that there has to be a solution to the linear system, and the linear system has to correspond to a positive semi-definite matrix. So remember this squiggly equality sign means that the matrix A plus lambda I has to be positive semi-definite. And again, right, that comes from the fact that if looking back up at the Lagrangian here, right, if A plus lambda I is not positive semi-definite, then the solution is also negative infinity to the minimization problem over x. Okay. So simplifying the dual objective function, just like before, I end up with this dual optimization problem. Right. So the complicating factor compared to the previous example was when the quadratic function is non-convex, and I have a convex constraint, right? It's possible that for certain values of lambda that it is a convex function, right? And in particular, that's always true here. As long as lambda is large enough, it's always possible to make a plus lambda I positive semi-definite. Let's check that, right? So recall that matrix is positive semi-definite if and only if for all x transpose A plus lambda I times x is greater than or equal to 0. Right? That would mean that A plus lambda I is positive semi-definite. We know, right, from that theorem about eigenvectors and eigenvalues that we saw, I guess, 2 lectures ago now, right? And the one that you're basically proving on the homework, that x transpose A times x, the largest that can be is x transpose x
times the maximum eigenvalue of A, and this and the smallest that X transpose A times X can be is equal to X transpose X times the smallest eigenvalue of A. So basically, X transpose A times X is bounded from below by the smallest eigenvalue of A times X transpose X. Similarly, X transpose I times X is just equal to X transpose X. So if I add lambda to it, right, I get that in this particular case, I get that this thing is always at least as big as the smallest eigenvalue of A. Oops, I shouldn't use lambda. I use mu. Call it mu min times X transpose X plus lambda times X transpose X. It's at least this big, where mu min here is the smallest eigenvalue of A. So as long as lambda is greater than or equal to the smallest eigenvalue of A plus lambda I will be positive semi-definite. Another way to see this argument, if you don't want to use that X transpose A times X is greater than or equal to the smallest eigenvalue times X transpose X, we can actually just explicitly construct the eigenvectors and eigenvalues of the matrix A plus lambda I. So let's do that. So let's suppose that X is an eigenvector of A. So that is that A times X is equal to mu times X for some mu. Then A plus lambda I times X is just equal to, well, X is an eigenvector of A, so this is equal to mu X. And X is also an eigenvector of the matrix lambda I, right? Because everything is an eigenvector of the identity matrix. So the second term is just lambda times X. So that tells me that if X is an eigenvector of A, then X is also an eigenvector of A plus lambda I, only its eigenvalue changes from mu to mu plus lambda. So the eigenvectors and eigenvalues of A plus lambda I are the same as the eigenvectors of A, and the eigenvalues shift by lambda. So so the same argument here, right, that I just showed before, right? A plus lambda I will be positive semi-definite, right, as long as lambda is at least as big as the smallest eigenvalue of A, because in that case, when you add it to at least as big as the smallest eigenvalue of A, I guess negative value of that, because when you add that to mu, you'll get 0. Right? We need that mu plus lambda should be greater than or equal to 0, right? So lambda has to be greater than or equal to a negative mu. And this should be true for for all of the eigenvalues. So as long as lambda is greater than the negative of the smallest eigenvalue, the system will be positive semi-definite. So as an example, right, if A has its smallest eigenvalue is -1, if lambda is at least as big as 1, the matrix A plus lambda I will be positive semi-definite. So this is actually sort of just a nice observation in general. It's not always easy to figure out what the eigenvectors and eigenvalues are of a sum of matrices, but it is always easy to figure out what the vectors and eigenvalues are of matrix A plus lambda I. And it kind of makes sense, right? That this is almost, it's almost like the definition of the eigenvectors and eigenvalues, to be honest. So it makes sense that it just should shift a little bit. All right, so this is a pretty complicated dual problem, right? Again, we could replace the second constraint with some with some expression that says that, like, just like we kind of did before, right? Try to turn there exists an x such that a plus lambda I times x equals minus b. Right? We could turn that into a convex constraint. But we still, of course, would have this a plus lambda I greater than or equal to 0 constraint. So we can use you can eliminate the first constraint, the a plus lambda I, positive semi-definite. Right? We can turn that just into lambda has to be greater than or equal to the negative of the smallest eigenvalue. Right, so we don't actually have to end up with a semi-definite programming problem here, which is much more of a pain to deal with than sort of the standard, linear or quadratic inequality constraints that we're sort of used to seeing. We get rid of the second term by basically making the same argument we did for the previous case. Okay, so I think I just made this argument. So again, right, we can eliminate the positive semi-definite constraint by making this with this constraint that just says that as long as lambda is large enough, right, the matrix will be positive semi-definite. So once the matrix is positive semi-definite, right, then our next concern is eliminating this second constraint that a plus lambda I times x is equal to minus b. To do that, we can again use the same argument as before. So I have it kind of all written out here on the slides already. So I'll just go through it quickly. If I can get my touch screen to advance. Okay, so again, right, there's a solution to this linear system if and only if minus b or b, it doesn't matter which one we look at, is in the span of the eigenvectors of a plus lambda I, span of the non, whose corresponding eigenvalues are non-zero, right? So again, the constraint here is, right, that you can't have anything, minus b can't have any components along the along an eigenvector of a plus lambda I, which is just an eigenvector of a. You can't have any non-zero component along one of those eigenvectors if the corresponding eigenvalue is equal to 0. So if that's the case, right, then the objective function, right, which looks like b transpose a plus lambda I pseudo inverse plus times b, can be written in the following very aesthetic form. It can be written as the sum over xi transpose b squared divided by lambda plus mu I. The reason for that is that the characterization of the pseudo inverse, right? So remember, if a plus lambda I is positive semi-definite, right, then its pseudo inverse, right, so let's say it's equal to, I don't know, I can use q d q transpose, right, for some orthogonal matrix q, and diagonal matrix D. This is just equal to q d plus q transpose. That's just the construction of the pseudo inverse. So the only difference between these two quadratic forms then is the eigen values, right? So in the pseudo inverse, right, I just basically invert all the non-zero eigenvalues. So to get this reformulation, I use this fact. So I can write b transpose a plus lambda I as b transpose the sum over all I of mu I. Stick with the previous notation, mu I xi transpose, or this is just 1 over lambda plus mu I, because we invert the non-zero thing. So this is only for the eigenvectors such that lambda plus mu I is greater than 0. times b, right? So anything where lambda plus mu I is equal to 0, right, has a 0 eigenvalue, right? So b transpose, that term will just be 0. It has a 0 coefficient. Then b transpose this thing is, well, just xi transpose b times b transpose xi, which is just xi transpose b squared. So that's how I get this. That's how I get this formula here. So this is only the case, right, if b, when projected onto the eigenvectors of a plus lambda I, doesn't have a non-zero component along some eigenvector with a 0 eigenvalue. So if it does, right, then the solution is, the solution of the optimization problem will kind of be degenerate, right? We can make it, we can make things as small or as large as we want. In fact, we can kind of see this from this formula, right? As lambda plus mu I gets close to 0, right, the ith term in this sum is approaching infinity. So back in the objective function, if I slide back to the objective function here for a second. Oh man. Figure out what's wrong with this for the next lecture. Substituting back in, I can actually turn the whole objective function into a convex function if I do the following thing. I'm going to define some new function. I'm going to call it f of lambda, where f of lambda is equal to infinity if there's some eigenvector xj such that b transpose xj is not equal to 0 and lambda plus mu j is equal to 0. Right? So there is some mass on an eigenvector that has a 0 eigenvalue, then I'll define f of lambda to be infinity. And otherwise, it's just that quadratic form that we just saw, right? It's the solution to the b transpose a plus lambda I times b, just by evaluating that and using the eigenvalue decomposition. And this function f of lambda is sort of like the appropriate extended value definition of this expression here. Like I said, because as lambda plus mu I gets close to 0, this function approaches infinity, right? So it's the correct sort of extension. It's easy to check actually that this bottom function is convex, or concave. Plug it in, it's convex, but when you plug it in, it's the negative of that. So we get a concave function. And so as a result, in the dual formulation, we're just basically minimizing minus f of lambda minus lambda, subject to the constraint that lambda has to be greater than or equal to minus mu min. Right? So this lambda has to be at least as large as the negative of the smallest eigenvalue of the matrix A. Okay, like I said, this was this was sort of the we were building up today from like a very simple example of optimization problems that were relatively easy to handle, and sort of building to more complicated ones. So just as a sort of a final remark before we stop today's lecture, how would you solve this optimization problem, this dual optimization problem? So it's a maximization problem of a concave function subject to two constraints. Right? Lambda has to be greater than or equal to 0. Lambda has to be greater than or equal to the negative of the smallest eigenvalue. How would you solve this optimization problem? Everyone's just lost. Nobody has any idea, which could be. You could do projected gradient descent here, right? Because it's a constrained optimization problem.
You can actually cheat a little bit though, because this is a univariate optimization problem, right? Lambda's just, there's only one lambda here. It's not a vector. It's just a single number. So we could actually just sort of binary search to find the solution. Just like we would do line search, right? Because we're effectively just looking at, we're just trying to find a place where the derivative is equal to 0, right? And the constraints are satisfied. Basically, the solution will be at a place where the derivative is equal to 0, because as lambda gets close to its boundary, so it's either going to be a solution where lambda is equal to 0, lambda is equal to minus mu min, or some place where the derivative is equal to 0. If there's a place where the derivative is equal to 0 that satisfies those constraints, that will be the solution. And otherwise, it's just lambda on the boundary. So we can just binary search to find the solution in this case. Okay, so let's stop there for today.